In example 2 from the same page, we're looking at some inclusive events. What they want to know is, what's the probability that someone chosen at random is a man or opposes the change? Alright, now you can be a man and oppose the change at the same time, so those are inclusive events. So the way you do it is you have to look at the probability that the person chosen at random is a man. Well, that's 50 out of 100. Plus the probability that the person chosen will oppose the measure, and that's 37 out of 100. But then you have to not forget to subtract away the probability that a person is both a man and opposes the change, and that's 12 out of 100. So 50 plus 37 minus 12 gives you 75. So it's 75 out of 100, or 75%. Alright, so those two examples I think really highlight the difference between inclusive and exclusive events. Alright, we're going to move on to something called complementary probability, and this is really useful. You know how complementary angles both add to 90, right? Well, in complementary probability, you have two or more probabilities that add to 1. Okay, and 1 is 100%. And the probabilities for an event, for all the possibilities that could happen in an event, all have to add up to 1 or 100% all the time, because something has to happen. Right? Something is always going to happen. So for an example, a really simple example, maybe the probability that I will return to Tana this week is 42%. Just making that up. Then, well, what's the probability that I won't return this week? Well, it has to be 58%, because either I will or I won't. Either I do or I don't return this week. And so those two possibilities, the probabilities of them, have to add to 1, or 100%. They're called complementary events. I like to think of it as the big potato. This big potato represents everything that can happen, 1, or 100%. And if I split it up into two logical possibilities, I return this week or I don't, you see how they have to fill the whole potato. They have to add up to 100%. More generally, the notation that's used is the probability of event A and the probability of event AC. AC represents the complement of event A. Okay, those two probabilities have to add to 1. The complement means every other possibility besides event A. In my example, event A was I return this week, and event AC, the complement to that is I don't return this week. Okay, those have to add up to 1. Those probabilities have to add to 1. And then there are two other little formulas you can derive from that by rearranging the terms. Okay, and so those three are all just saying the same thing. Here's a picture of a Venn diagram in your book that works through example 3. In example 3, what we're looking for is the probability that a club member chosen at random belongs to at least 2 clubs. You know, there are these 3 clubs there. Okay, so the fact that we're choosing a club member means that they have to belong at least to 1 club. I mean, that's what it means to be a club member. So if we say we're looking for the probability that they belong to at least 2 clubs, what we're going to do is we're going to use a little trick. We're going to use complementary probability to get at this sort of through the back door. If we think about the whole potato in this situation, at least 2 clubs. Well, the only other possibility is 1 club, right? Because if I belong to at least 2 clubs, then that could be 2 or 3. Well, what else is possible? Like I said, you have to belong at least to 1 if you're a club member. So the other side of the potato, the complementary event, is that you only belong to 1. So what we're going to do is we're going to say, look, the probability that I belong to at least 2 clubs is 100% minus the probability that I belong to just 1. If you take a look at that picture again, you'll see that there are 24 people that belong to just 1. You can add up the people that are only in a single colored circle, and that's 24. So if you subtract 100% minus that, you get 36. And then there are 60 people total, so 36 out of 60 happens to be 60%. Okay, well, you might be thinking this is really stupid. We could have done this a lot more directly by just directly counting up the number of people that are in at least 2 different circles or 2 different clubs in that diagram. And that's fine, that will work. And you will get 36 out of 60, and you'll get the same answer. But the point is that there is another way to do it. This complementary trick is sometimes a big advantage to the direct way. And I want to show you a really famous example of a situation like that. This is the famous birthday problem. There are 19 of us in this Algebra 2 class, well, not counting me, now that we're all together. So what's the probability that at least 2 of you guys have the same birthday? I know you might be saying, no, we know each other, we don't, but anyway, theoretically, if it's just a random sample of 19 people, what's the probability that at least 2 people have the same birthday? Alright, whenever you see the words at least, it's sort of an invitation to use this idea of complementary probability. In this case, it's much easier to do it that way, because at least 2 means it could be that 2 of you have the same birthday, or 3, or 4, all the way up to 19 of you, all 19 of you having the same birthday. And so we could find out all of those possibilities and add them up. Or we could subtract from 100% the other logical possibility. And what is that? The whole potato is either at least 2 of you do have the same birthday, or no pair of people or more have the same birthday, or your birthdays are all different, right? If it's not true that at least 2 of you share the same birthday, then all your birthdays must be different. Okay, so what we're going to do is try to find out the probability that you all have unique birthdays and subtract that from 100%. And the way this works is to first start out by just picking someone. Okay, I look at the top of my alphabetical list and there's Victoria's name. The chances that her birthday is unique, well, it's 365 out of 365. We only have one person. Now if we add Tishan to it, the chances that his birthday is unique from Victoria's, well, she's already got one day, so he only has 364 possibilities that are unique out of the 365 days, right? And so on. If we add a third person, let's say Gautier, the chances that his birthday is unique and different from Victoria's and Tishan's is just 363 out of 365 now, because they've already taken 2 days. And then as we add another one, let's say Aiden, she only has 362 unique days to choose from, etc., etc. So the chances that all 19 of you have unique birthdays, this is an and, right? And so I need to multiply all of these. And so it's going to be the product of all these fractions. 365 over 365 times 364 over 365. All the way down, you can count out 19 of them. You should end with 347 over 365. This is looking hard, right? But luckily there's a shortcut. If you look at what we have, we multiply all these fractions together, the numerator is going to look like this. And that, if you look back, is actually 365p19. And in the denominator, we have 365 to the 19th. Okay, now if we divide those two using our calculator, we're going to get 0.62 roughly. So the chances that all of your birthdays are unique is 62%. Logically, and this is the trick, then the chances that at least 2 of you share the same birthday are going to be 1 minus 0.62, which is 0.38, or 38%. Which is actually kind of surprisingly high, I think. It kind of goes against my common sense. Anyway, so the chances that at least 2 of you have the same birthday are 38% in this situation. If you wanted to apply this to a different situation, I sort of made up a formula for that. Okay, the chances that at least 2 people out of a group of n, in this case n was 19, share the same birthday are going to be 1 minus 365pn over 365 to the n. Right, now this is hard, and I don't expect everyone to totally understand everything that just happened here. But what I hope stood out and sinks in is that sometimes using the idea of complementary probability can make a problem doable when otherwise it would be nearly impossible. Okay, to do this the other way would have literally taken like hours and hours. All right, guys, it's time for me to set you loose on some work. So this is a lot, but I think this kind of stuff is confusing and it requires a lot of practice. Many of the early examples start off quite simple, and I think that will help. Page 656, 1 to 49 odd. Remember, when they start talking about a number cube, that's just the die thing with the 1 through 6 on it. Good luck, guys, and send me lots of questions if you need help.